Okay, so in this video I decided to show a little bit about this tool and new updates I have been making there. So now when we open it, it will send this command like this, and then the microcontroller, it will return all these parameters that can be locked, and then it will also answer always after we ask something. So if we example press this enable driver, it will send enable driver, and then MCU will answer here that it was success, and we can disable driver, and it will also answer for that. So now it's using this kind like ACK and NACK protocol, so it always answers, so it's like synchronous. And then we can start the motor, and we can hear this sound. We can go to start logging. So here we can zoom, and we can actually see the signals. So if we example, we can turn some of these signals off. So if we want to check only these, so these are used for this rotating HFI, so it will detect the motor position with this signal. So this is actually I can plot this one. So this is now telling us the rotor position, and if I rotate the motor, we can see, I have to turn this off. So this orange line is showing the current motor position, and it's like completely sensorless, and it's only using this phase wires to estimate that. So we can go back to this, and I will actually plot only like one of these. Maybe I can plot this alpha signal. So new thing here is that we can go to settings, and here I have some different these systems, and if I click this read from motor, so it will actually read these parameters from the motor, and it updates them here. So currently we are using this rotating HFI, and here we have the HFI the amplitude, and we can go and reduce this and just right here, and we can see it like changes this. So now the acoustic noise is much lower, and we saw that this amplitude went down, and now it's even more down. So that way we can like in real time change this, and I can set it to rotate now, so I will apply 4 amps here, and now with this sensorless HFI it doesn't like start losing its position, and it can rotate at very slow speeds and even stand still. And now I will put something more here like 12 amps, so now it will produce even more torque. But then there's also other thing, so I will disable driver now, and I will plot maybe the this, let's see, so we can plot this. So now I'm going to show this another HFI method. So here is also this pulsating HFI, and we can write it to the motor, and if we start now, instead of rotating HFI, it will be using this pulsating. So this is now the pulsating, and we can already see the signals is a little bit different than previously. And actually I'm going to show, instead of this, I will show this. So now we again have the same orange line is showing the rotor position, and we can apply some current here, and it will start to rotate. we can go back here, and sometimes there is this small bug still in this system. I had to fix that. But we can go here, and if I stop logging, so for this pulsating HFI I'm actually using a little bit different system. So what it does, it will on this pulsating HFI it will inject this D current. It's showing this blue, so that is the like measured, and then it will also estimate this ID ripple. So that is, this estimation is used because I have to know this high frequency current, and with this estimation we can remove it from the signal. I don't remember if this was correct. Well, I think I'm not plotting it here, but other thing I can show for this pulsating HFI, so how this thing works. So what the system is doing, it tries to keep this leakage, this IQ current at 0. So it's like going both sides of this 0 amps, and what it does, it's trying to keep it 0. But if I rotate it very fast, we can see it is moving like that. And how this is solved, so in this HFI current, it's actually like measuring the slopes of the, I can also plot that. So if we go somewhere here, so what this method is actually doing, so these small ripples, it's actually like taking this kind of like least square line fit from those, and it will calculate the slopes, and that way it will adjust the estimated position so that this IQ amplitude is as close to that 0 as possible. But another thing I can show is we can go this ID measured, and if we look, we can see that it's actually like pretty stable, this kind, and I can actually go also and plot this HFI index. So the HFI index in normal mode, it's going between 0 and 9, so it has only 10 index. And if we look this HFI IQ amplitude, it's also going like, it goes up and then it goes down. But the thing that I can show, I move that away. So if we look the ID measure, it looks like very stable, and we will hear like that whining sound, but there is this kind of like spectrum spread. So I will also plot this. So if we activate this, what it does, it removes the whining sound, because it will like spread the spectrum away from that 1 kilohertz, so it will randomly make the slopes like longer and shorter, and this way you don't hear this kind of like whining sound, and instead you hear this kind of like white noise. So this can be also used and the accuracy is still same, and we can even remove the reduce this amplitude a little bit, and then it will be like very quiet also. I will also try to make this even better, and it should be like totally quiet, and I think that should be possible for the next PCB, but this for this current PCB it's not working that well yet, but for the next PCB it should be possible. But yeah, so that's how it's using this pulsating HFI and rotating HFI, and at some point I'm planning to also implement this kind of like vector HFI, and then there is some other stuff, and then I'm planning that this firmware flashing from this software. Yeah, thanks for watching.